4 squared plus 4 squared equals c squared. That's 16 plus 16 equals 32. The square root of 32 is about 5.6. That is how I add those two vectors together. Okay? But a vector isn't just a number. A vector is a number with direction. So I have to have the direction for this as well. This 4 newtons is going north. If you want to call that north, you might want to call it up or 9 degrees up. This 4 newtons is going to the right or to the east or to the or at 0 degrees. We need to have a angle for this guy right here. That is our direction. And the way you get direction for any vector, just about, it's going to be our angle is our direction, is equal to, well, let me say this real quick. Hold on, erase that. We have, if the tangent of an angle is equal to y over x, or sine over cosine. All right, remember our, you know, from pre-cal, that tangent is sine over cosine. Well, 99 times out of 100 in math or any science, our sine is y and our cosine is x. So I'm just gonna say y over x. So the tangent of an angle is y over x. That means the angle is equal to the arctan. The arctan of y over x. So then, what am I going to write down for this problem over here? The arctan of what? What's my y component?
4,
Okay, and what's my x component?
6.
No, it was also 4. It was 4 and also 4. Okay, I have two different problems here. I'm sorry. I have this problem over here. I have this problem over here. We'll get back to this in a second. Okay. We have the arctan of 4 over 4. And that simply is over here, arctan, and then your calculator, just press tan twice. Arctan of 4 over 4. Ooh, that's weird. I'm not wrong. Four over 4. Why is it doing that for this? No, I'll do it on the Google calculator. That works. Arctan of 4 over 4 in degrees. Okay, 45 degrees. So that is this over here. When I add 4 newtons this way and 4 newtons this way, that gives me 5.6 newtons at a 45-degree angle. Okay. A squared plus b squared, that's 4 squared, boom, plus 4 squared, boom, is equal to c squared, which is 32. 16 plus 16 is 32. The square root of 32 is 5.6. That's just my magnitude. To have a direction, I have to have an angle as well. To get my angle of any vector, it's going to be the arctan of the y component over the x component. In this case, our y component and our x components were both 4 newtons. So let's say that's 4 over 4. And that comes up to be 45 degrees. So my entire vector is 5.6 newtons at a 45-degree angle, which makes sense because 45 degrees is halfway between 0 degrees and 90 degrees. And they're both 4 newtons. 4 newtons 4 newtons on a 90-degree angle, 4 newtons on the x, the 0-degree angle on the x-axis. And so that means I have equal x and equal y. I have 4 newtons on x, 4 newtons on y. That means our angle is going to be split between the two evenly. Question: if it were 6 newtons on the y and 4 newtons on the x, do you think this would be greater than 45 degrees or less than 45 degrees?
Less. Yeah.
Okay. So let's see. We said 6 on the y, right? And 4 on the x. That's 56 degrees. All right. So that's more than 45. How could I just know that it's more than 45? Well, let's think about it. If it were 6 newtons this way, I really hate writing with the mouse. If it was 6 newtons this way and 4 newtons this way, I have more on my y than I do on my x, right? That means that I have more on my y than I do on my x. That means it should be above 45 because it's closer to the y than it is the x. Okay? If I have 1, 2, 3 on my y and 1, 2, 3, 4, 5 on my x, do you think it's above 45 or lower than 45?
Would it be lower?
It will definitely be lower because this, when I add these two together, it's closer to the x. All right. This guy plus this guy is going to be this guy right here. You know what? Yeah, 3 plus 5, that becomes, let's get the actual number. Let's do it. Oops. Let's actually do it. That's 3 squared plus 5 squared is equal to c squared. And that is 9 plus 25 is equal to 6c squared, which is, what is 9 plus 25? 34. 34 is equal to c squared. Therefore, my actual vector, when I add the two together, is the square root of 34. Square root of 34. 5.8. So 5.8 is the magnitude, the number. Remember, vector is number and direction. So I have 5.8 right here. That's my number. My direction is going to be the angle. How do I find the angle? Tell me, how do I find the angle?
Tan arctan y over x.
What's my y?
3,
What's my x?
5.
Over 5. And you predict this is going to be above or below 45?
Apple no bit below.
Below 45. So let's see. Arctan 3 over 5 in degrees. Below 45. It's about 31 degrees. Good. About 31 degrees. So when I add this guy and this guy, that is a 31-degree angle. 5.8 newtons.
So when the numerator is lower than the denominator, then it's below, and when the numerator is greater than the denominator, it's above.
Correct. But the better way of thinking about it is when the y is greater than the x, the angle is closer to the y. When the x is greater than the y, the angle is closer to the x. Got it?
Yes.
Okay. Now going back to this guy over here. This is me adding these two vectors that are already on this 4 newtons, or the 6 newtons rather, was directly on the x-axis, y-axis rather, and this 4 newtons was directly on the x-axis. But what happens when I have two vectors that are acting on both axes? Okay? This guy is on both the x and the y. This guy is on both the x and the y. How can I add them together? Well, you have to break them down into their x and y components, which means I have to have my x components, this guy, and my y components for this guy. I have to have my darker blue x component for this guy. Oh, I went out too far, sorry. Not right there. And honestly, I should add these numbers backwards. Let's make this one 4 and make this one 6. So I have my x component. How far out on the x does this vector act? So this vector has an x component. It also has a y component. Comes down this way. X and y, we have this triangle right here. This triangle down here, boom. And I have this triangle up here. And I want to add these two triangles together. Or really, I'm sorry, I want to add these two vectors together. But the only way to do that is to add their x and y components up individually. So then how do I break this down into its x? This is, well, x is always what function? Typically what function? How do I what trig function rather is typically the x, the horizontal?
Sine?
Cosine?
Cosine. Cosine is the horizontal. So that means that this is 4 newtons cosine what? 30. 4 newtons cosine 30. Just type that into the computer or calculator. 4 cosine 30 degrees. It's about 3.46. All right. 3.46. All right. And then over here, this is going to be what? Right here, what's the side going to be?
Wait, what's your question?
All right, so I have this vector, this black vector going down here, 4 newtons at a 30-degree angle below the axis. It acts on both, since it is at a 30-degree angle, it's acting on both the x-axis and the y-axis. If this is 4 cosine 30, what's this over here?
4 sine theta.
And theta is what?
30.
30. Good. And I know that sine 30 is 1/2. Half of 4 is 2. Which means 2 newtons plus 3.46 newtons is equal to 4 newtons. How is that the case? How do I say that 2 plus 3.46 is equal to 4? Well, they're not on the same axis. This is on the x-axis. This is on the y-axis. That means that you have to add them up with the Pythagorean theorem. 3.46 squared. That's my x. Plus 2 squared is equal to c squared, which should be what? These two should come out to be about 16. Okay, because 4 squared is 16. So this is obviously 4. 2 squared is 4. 3.46 squared. No idea what that is. 3.46 squared. It's about 11.97. I'm just going to say 12. I did some rounding, so I'm going to say 12. All right. 12 plus 14 is equal to 16. Hey, it works out. Square root of 16 is 4. This x plus my y when I add them up with the Pythagorean theorem, gives me this guy right here. A squared plus B squared equals C squared. Okay. So I have a 4 Newton force acting at a 30-degree angle below the axis. That means that it's 3.46 pushing to the right and 2 pushing down. The same thing up here. I break this guy into its X and Y. What do I write down for my horizontal up here? What is the horizontal for this triangle up here?
Or cosine 30.
Or cosine 30? Oh, I'm sorry, it wasn't 4. This one's bigger. This is 6. This one was 4. I'm sorry, this one's 6. So I'll change that real quick. My bad. Like that. I can't make it smaller. It's weird. There we go. 6 cosine 30. And what's this up here?
6 sine 30.
6 sine 30. Okay, I know for a fact that sine 30 is 1/2. Half of 6 is 3 newtons. And then cosine 30 is not 1/2. So I'll just throw it into the calculator. I think it's like square root of 3/2, I think. I can't remember. All right, but regardless, I'll throw it in the calculator. 6 cosine 30. 6 cosine 30 degrees. Make sure it's in degrees. Is about 5.2. Say 5.2. Which means if I have a 6 Newton force acting at a 30-degree angle, that means that 5.2 newtons is pushing to the right and 3 newtons is pushing upwards. Okay. I can change that 6 Newton force. I have 6 newtons. That's how hard I'm pushing something. I can push it at a 30-degree angle. I can push it at a 45-degree angle. Okay. In fact, let's try that real quick. I'm just gonna say right here, I have still a 6 Newton force, and now it's at a 45-degree angle. I want to break it down to its X and Y components. I have my X components, and I have my Y components. All right, before I do the math, question. Do you think my X component at this 45-degree angle is going to be less than or equal to this 5.2 X component at a 30-degree angle?
Equal.
Equal?
Wait, no. Wait, can you repeat it again, please?
Okay. I have a 6 Newton force. This is 6 newtons, and this is 6 newtons. I'm just changing the direction of where I'm pushing. So if I imagine I have a pool stick, okay, a cue stick for playing pool, billiards. I can push a ball with 6 newtons of force. Here's my ball. I'm hitting it at a 30-degree angle, or I can hit it at a 45-degree angle. They're both getting pushed the same force. The question is, how much that force is acting on the x-axis and how much that force is acting on the y-axis. Do you think that me pushing this 6 Newton force at a 45-degree angle is going to be, do you think the x-axis over here, it was 5.2? Do you think that this is going to be greater than or less than 5.2? It's not. I'll go ahead and tell you it's not equal.
Less.
Why do you say that?
Because there's more on the y-axis.
All right, you are correct.
It's closer to the y-axis.
Excellent. So we have, this is going to be, what's the equation for the x-axis?
6 cosine 45.
6 cosine 45. Cosine 45. And this is going to be 6 sine 45. 6 cosine 45 is about 4.24. 4.24 newtons. Now, without doing any math in your calculator, tell me, could someone tell me what 6 sine 45 is? I'll give you a hint. We talked about it. Just go ahead. Go ahead. What do you say?
6.
No, it's not 6. I talked about it over here a little bit. Where was it? Talked about it right here. We said that it was if it's between 0 and 90, if it's closer to the x, it's below 45. If it's closer to the y, it's above 45. My angle over here is 45. Can you tell me what this is equal to? No worries. Let's put in the calculator. 6 sine 45 degrees. Hey, look at that. It's the same thing, 4.24. Okay. Why is it the same? Why is 6 sine 45 the same as 6 cosine 45? Why is 6 cosine 45 the same as 6 sine 45?
I think because it's not close to the y-axis and it's not also close to the x. No, it's close to the y-axis, but it's just at an angle in the middle, because you said that it would be above 45 degrees if it is above. Yeah.
Excellent. So 45, if the x-axis is hey now. Sorry. The x-axis is 0 degrees, the y-axis is 90 degrees. 45 is right in between. That means that they are equal x and equal y. Okay? And it's still true what we said. We said that what's going on? Can y'all hear me?
Yes, we can.
Okay, something happened. Hold on. Ow, 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 stop. I'm watching this cat for someone. Hold on. And he stepped on my computer and now everything's frozen. What to do? Oh wow, what happened here? Oh, tab maybe? Control Alt Delete? There we go. Cancel. Task manager. Okay, there we go. Okay. Y'all can see my screen, right? Can y'all hear me? Still?
We can
Yes,
see
we
your
can.
Okay, all right. Sorry about that. So we have equal parts for x and y because at a 45-degree angle. Okay, so it's 4.24 and 4.24. And it's still true. We said that, hey, we asked you if it's going to be less than 5.2. Over here, we have 6 newtons at a 30-degree angle. And that means that we have 5.2 on the x-axis. And I asked you, do you think it's going to be less than 5.2 on the x-axis over here? And yeah, it is. It's 4.24. So that's true because it's closer to the y. But it's also equal distance from the x and the y since it's at 45-degree angle, so they are equal to each other. And over here, 5.2 squared plus 3 squared is equal to 6 squared. Over here, 4.24 squared plus 4.24 squared is going to be equal to 6 squared. So let's do that real quick. We have 4.24 squared plus 4.24 squared is equal to, well, let's figure it out. 4.2 squared is equal to 18. All right, let's say 18. C squared means that 18 plus 18 is equal to C squared. 18 plus 18 is 36. C squared. And the square root of 36 is equal to 6. This side plus this side through the Pythagorean theorem is equal to this side. All right. So let's take it back to the original question. How do I add these to this vector, 4 newtons below, 4 newtons 30 degrees below, and 6 newtons 30 degrees above? I break it down into its x and y components for both. And I have an x components and an x component. Remember what I said at the beginning? If they're on the same axis, we can add them up directly. So I have 5.2 newtons on my x up here. And I have 3.46 is the sum of my x. All right. 5.2 on this x. And then 3.46 on this x. 5.2 plus 3.46. 8.66. You got with me on that? Yay or nay?
Wait, so sorry. So this is just like the addition of the x and the y angles to make the addition, just the addition of them vectors.
Yes. All right, cool. So imagine, I'll give you a real example. I'm taking the same problem. All right. Here's a box. All right, table. And imagine you're looking down at the table. So I have a person here. I have a person right here pushing the table this way with 6 newtons of force. All right, and I have a person here pushing the table this way with 4 newtons of force. All right, 4 newtons of force. They are both pushing at a 30-degree angle. It's just that this guy is above. This is 30 degrees. And this guy is below 30 degrees. The question becomes, since they're both pushing on this table, which way is it going to go? Obviously, it's still going to go to the right. Using just what you know, if this guy is pushing harder, they're both pushing the 30 degrees. They're both pushing to the right. The table is obviously going to go to the right. Do you think it's going to go right up, completely right, or right down, based on these numbers over here?
Right up.
Why do you say that?
Because 6 is greater than 4.
Excellent. That's exactly right. So that means that when I come over here, I have 5.2 on my X. Cool. And then 3.4 on my X. That means that this guy is pushing to the right with 5.2. I'm sorry, 3.6. And this guy is pushing to the right with 5.2. This, we do it for the Y. We do it for the Y. That's going to be the big ones first. 3 newtons on my Y plus lighter one. 2 newtons on my Y. That's simply equal to 5 newtons. Okay. So on my X, on my X, I am pushing with a total force of, oh, I'm sorry, I messed up big time. Where did I mess up? Where did I mess up? Did anyone catch that?
I did 3, but I don't.
Okay, so you're right. I have 3 right here. I have 3 on my Y on this guy, and I have 2 on my Y on this guy. But where did I mess up? What did I do wrong?
You didn't put the X value for the upper one.
I don't need the
Which
X just I don't need the X just yet. I have my X right here. All my X's are right here. The sum of the X's is 5.2 for this X and 3.46 for this X. I'm only worried about the Y. Where did I mess up on the Y? Anyone see it?
And are you talking about like in your equation?
Yeah. I said 3 newtons plus 2 newtons. What's wrong with that?
Huh.
This guy is going up. This guy
Oh,
is
is it
going
negative?
down. It's minus 2 newtons. Excellent. Which means the sum of my Y forces is equal to 1 Newton. All right. That means I'm barely pushing on the Y-axis at all, which makes sense, right? Because this guy is pushing down and this guy is pushing up. He's only pushing slightly stronger than this guy, so it's going slightly upwards on the box. Does that make sense?
Yes, it does.
All right.
Yes.
All right. So this guy's pushing down, this guy's pushing up. That's 3 is going up, 2 is going down. That comes to be 1. So I have the 2 X's, they're both pushing to the right on the X on the horizontal. So those add up together. But one guy is pushing down on the Y, the other guy is pushing up on the Y, so they work against each other. So I have 8.66 newtons on my X and 1 Newton on my Y. How do I put these two together? I have 8.6 on my X, and 1 on my Y. How do I add them up together? If they're on the same axis, I can add them up directly, like I just did. 5.2x, 3.46x. That comes up to be 8.66x. Same thing for the Y. 3 on my Y, -2 on my Y. That comes up to be 1 on my Y. But if they're on separate axes, how do I add them?
Pythagorean theorem.
Pythagorean theorem. So I have 8.66 squared plus 1 squared is equal to 8.66 squared. About 75. Let's say 75. Uh, 75. Oh no, sorry, let's do that wrong. It's equal to C squared And that is 75 plus 1 is equal to c squared, because 8.66 squared is 75, and 1 squared is still 1, which means that 76 is equal to c squared, which means that the square root of 76 is about 8.72. All right, 8.72. I'll do it like this to be better. 8.72 newtons. So I have a guy pushing with 4 newtons and the guy pushing with 6 newtons. 4 plus 6 in this case is going to be equal to 8.72. Now, I need a direction because this is a vector. A vector is a number. 8.72 newtons is my number and direction. How do I get my, I'm sorry, I said that wrong. I said something wrong. Let me rewind. I'm sorry. I have 8.66 newtons and 1 newton. That's better. 8.66 newtons plus 1 newton is equal to 8.72 newtons. Okay. This guy plus this guy is equal to this guy. And it's only because of the Pythagorean theorem does this guy plus this guy equal 8.72. Okay. Now.
So do 4, 6, and 8, like, why are we able to put that into the Pythagorean theorem? Like, I get that it equals 8.72, but like, why do we use the Pythagorean theorem if those are not like making
good question.
Right.
All right, cool. So I have this guy is acting on both the x and y because he's acting downwards on the angle. This guy is acting on both the x and y because he's acting on the upwards on the angle. Okay. The only way that I can add them up together is if I break it down into the x and the y. So there's 2 different forces. All right. I need to break them down to the x and the y. And that's what we did over here. This guy is 3.46 on the x, and this guy is 5.2 on the x, which comes out to be 8.66 on the x. So I took this guy's x and this guy's x, that's 5.2 and 3.46. This guy is pushing with 5.2 on the x. This guy's pushing with 3.6 on the x. Got that backwards, whatever. The total x for these two is 8.66. Okay. This guy is pushing up on the x with 3. This guy's up on the y with 3. This guy is pushing down on the y with 3. With 2 rather. 3 minus 2 is 1. So my total x for both of these guys is 8.66. My total y for both of these guys is 1. So I have all of my x and all of my y. If I were to draw it out like this might make it a little bit clearer. This is all of my x, which is about 8.66. And this is all of my y, which was 1. In other words, these 2 x's add up together, and we get a big 8.66. These 2 y's, one's going up, one's going down, they go against each other. So, but since this guy is pushing slightly stronger, it's not 0, it's 1. If I want to figure out what the actual direction is and what the actual vector is, it's my x and my y come out to be this right here. And this is a squared plus b squared equals c squared. And when I
Okay,
did that, sorry, go ahead.
that makes sense.
Okay, cool. And when I do that, that is 8.72 newtons. Okay. And that's my number. But a vector is number and direction. How do I get my direction for this? How do I always get my direction?
Arctan.
Arctan. So I'm going to do the, I know it's getting kind of crowded over here. Let's go do it down here. No, I'll do it over here. It's going to be the arctan of, it's always my, well, almost always my y over x. What's my y?
1.
1. Okay. And what's my x?
8.66.
8.66. No idea what that is. Arctan 1 over 8.66 in degrees. About 6.58 degrees north of the horizontal. And that makes sense. About, what was it? Let's say 6.6. Right. About 6.6 degrees. Which makes sense because that is a very tiny angle. So to sum up all that, we have I'll just draw it again. When I have a box and have a force going this way of, what's it again? Can't remember. A force going that way of 4 newtons, 6 newtons. 4 newtons, and a force going this way of 6 newtons. The y's are working against each other, but the x's are working with each other. This guy is pushing ever so slightly stronger than this guy. Therefore, it's going to go up and over ever so slightly. So if I had to guess, my arrow is going to look something like this. It's not really an arrow. I get the idea. But when I do that, the x's add up, the y's work against each other, and that means that 4 newtons this way and 6 newtons this way, they're both 30 degrees. Comes up to be 8.72 newtons this way, which is at 6.6 degrees. Got it? We're getting it better, rather?
Yes.
Excellent. I got
Wait,
chat.
so you found the x and y values using like the Newton cosine angle?
Yes, and it doesn't have to be Newton, it's any vector. As far as what you just said is correct, but it's not just for Newtons, it's for any vector. So really you can just say if I have a vector, that's the A stands for any vector. And I'm putting a hat over it, an arrow, a vector. All right. I can break that vector down into the x components. The x component is equal to the number of the vector cosine angle. And the y component is the number of the vector sine of the angle. It's not just forces, it's acceleration, it's velocity, it's momentum, it's any vector. But it makes most sense, I feel, with forces. Cool? Questions before we move on? Okay, cool. All right. Let's look at, that was all vectors. Let's look at a 2D problem. 2D projectile problem, rather. Where are they? Oh, I see how I upload it. Okay. Right here. All right, so this was not a force problem, but it's still a problem that's probably gonna be on the test. It's a vector problem, so you still have to worry about your x and y's. Okay. It says, let's look at number 5. It says a sharpshooter fires a .22 caliber rifle horizontally at 100 meters per second at a target 75 meters away. How far is the bullet drop by the time it reaches the target? Okay, so let's draw it out. In fact, I'll just do this real quick. Ooh, it's large. All right, so we have a gun. Guy shooting a gun. Boom. Okay. All right, as soon as that gun bullet comes out, what's acting upon it? What's going to happen to that bullet as soon as it comes out the gun? It's going forward, but is it only going forward?
Wind.
When that bullet comes out, it's going to make everything that falls. If I have a football that I throw up in the air, it makes a parabola. Okay. If I have a person drive a car off a cliff, it's a terrible cliff. If I have a car going off a cliff, it's gonna make a parabola, but only half a parabola. Okay. Everything that falls in a parabolic form. Okay. Same thing with bullets. You might not just realize it, but bullets are also falling. They just have a much wider base because they're going so fast. Okay. That bullet is going to make a half parabola form. Okay. Why? Well, here's my bullet. As soon as it comes out, what force is acting upon it? What's the only force acting upon it as soon as it comes out the gun? What force is pulling it down?
Gravity.
Gravity. All right, cool. Okay. So this is my free body diagram on the bullet. Okay. As soon as the bullet comes out, yes, inside the bullet, there was some type of force to speed it up. All right, so sorry, inside the gun, there was some type of force to speed it up. And so let's just say it was a spring that fires the bullet. Okay. The bullet was on a spring. Okay. And the spring pushes the bullet out and it goes. But once that bullet leaves the gun, that spring is no longer in contact with it. So the only force that's acting upon the bullet when it leaves the gun is gravity. That's it. Of course, there's wind, but we don't worry about wind too much in this class. And so it's going to fall. The question's asking, how far does the bullet drop by the time it reaches the target? Okay. Well, the target is 75 meters away. So maybe I didn't draw this quite right. Let me draw this a little bit better. Here is my targets. Target. I'll get the idea. Okay. All right, bullets is falling, and it would hit the ground, except for there's a target in the way. Okay. Sharpshooter fires a point of blah blah blah. It's traveling. All right, so let's just write down everything we know. And it's always best to do that whenever you have these types of projectile problems, because you have your x-axis, do it in blue again as usual. You have your x-axis, and you have your y-axis. What do I know about my x-axis? Well, the bullet was fired at what speed?
$100 meters per second.
100 meters per second. That's how quickly it was going when I fired the gun. But question, how quickly was it going up and down when I fired it from the gun? How quickly was it going up and down when I fired it from the gun? He fires it horizontally. So what's my velocity on the y-axis?
Zero.
Zero. This velocity on the y-axis is 0. And to prove that, I can show you real quick. If I'm firing it at horizontally, all right, the bullet's going all this way. What angle is this? What's my theta?
0.
0 degrees. Okay. And like I said earlier, the x component of this velocity is a vector, 100 meters per second. The velocity vector is equal to 100 meters per second at a 0 degree angle. Okay, cool. Well, I want to know my x components. My x component is the magnitude, which is 100, cosine 0. Question, what's cosine 0?
One.
Cosine 0 is 1. And 1 times 100 is 100. So my velocity is 100 meters per second on my x. And if I want to know my y, my velocity on my y is going to be 100 what?
Sine 0.
Sine 0, but what's sine 0 equal to?
0.
Sine 0, 0, and 0 times 100 is 0. You don't need the math to do that, but the math checks out. You can use your common sense. Hey, he shouldn't right here. It's not going up and down at all. So that means the velocity on the y-axis is 0. All the velocities on the x-axis is 100 meters per second. But the math also confirms it. Okay? Now, I can still shoot it. He can still shoot it at 100 meters per second, but let's say he raises it up a little bit. Okay? Would it still be going 100 meters per second on the x-axis and 0 on the y-axis? Obviously, no. What's going to happen to my x and y? My x is going to do what as he raises the angle?
Decrease,
Decrease. And my y is going to do what as he raises the angle?
increase.
Increase. Excellent. You got it. All right, cool. So going back to the problem, what do I know? I know that my initial velocity on the x-axis is 100 meters per second, and my initial velocity on the y-axis is 0 meters per second. What else do I know? What else do I know about what's the problem? Tell me. Read the problem.
We know the mass of the rifle.
We do, you're right. But I'll go ahead and I'll tell you that this is a and actually that's not the mass, that's the caliber. Caliber is like how strong the rifle is, right? But even if it were the mass, this is a kinematic problem, and kinematics doesn't really deal with masses that much. That wouldn't be important information. But what else does it tell us?
The
Delta
distance.
X,
Delta X is what?
75.
75 meters. What else do I know? What do I know about my Y? What's happening on my Y? What's happening on my Y? Someone help me out, yo. It's falling on my Y. And what rate is it falling at? Y'all still here? Oh no. What happened? Can I hear me? Okay. Yes. All right. All right. Yes. It's falling on my Y. And what rate is it falling at?
Negative 9.8.
Negative 9.8 meters per second per second. Okay. At what rate is it speeding up on the x-axis or slowing down on the x-axis? It's not. Gravity only works on the y-axis. As you can see from the free body diagram, the only force that's working on it once it's left the gun, the only force that's causing it to change its speed or direction is gravity. Gravity only works on the y-axis, therefore the acceleration on the y-axis is negative 9.8, but the acceleration on the x-axis, there's no force pushing it this way or that way. Acceleration is 0 on the x-axis. Cool. All right. I believe that's everything we know. How far does the bullet drop by the time it reaches the target? That's what we need to know. It's actually once you have everything written down, it's actually still a pretty tough problem because you have to decide what equations you need to use. Okay. Well, we need to figure out how far it needs to fall. We have to look for what variable is asking us to find. How far does it fall? What variable is it asking us to find?
Y.
Y. It's asking us to find delta Y. Delta Y is equal to what? That means we have to have an equation that has delta Y in it. There's only 2 equations that have delta Y. One of them is delta Y is equal to V naught T plus 1/2 A T squared. And the other one is V squared is equal to V naught squared plus 2 A delta Y. Okay. Which equation can I use? Honestly, I can't use either one right now. Which means I have to come over to here and figure out some more stuff. What can I figure out from this information over here? Oh, you know what? Let me rewind. Why can I not use either of these equations just yet?
There's no time given.
There's no time, so I can't use this equation. And why can I not use this one?
We don't know the final velocity.
You don't know the final velocity. All right. We don't know. We're looking for delta y, so that's our unknown. Both of these equations have two unknowns: our delta y and our t for this one, and our delta y and our final velocity for this one. Which means we have to come over here and see if we can figure out something else. This. Oh no, admit. What can I figure out from this information right here? Well, let's grab our equations. We have delta x is equal to v naught xt plus 1/2 a xt squared. We also have v squared is equal to v naught x squared plus 2 a delta x, ax delta x. Which equation can I not use at all? I'm going to say I can't use this equation right now. Why? Well, what is my acceleration on the x-axis equal to?
0.
All right, that goes to 0, which means that v squared is equal to v naught squared. And that's true. That tells me nothing. All right, it is true that on the horizontal axis, the x is not changing. In fact, I can show that to you as a animation. That's projectile. On the x-axis, if I have a projectile right here, I'm going to show you my components of my velocity vectors. I'm going to go in slow-mo. What's happening to my x? Hey, it stays the same size the entire time. All right, but what's happening to my y? It gets smaller, 0 at the top, and gets larger as it goes down. What this means is my x velocity is constant. My initial x velocity is the same as my final x velocity, which is what I have over here. My vx squared is the same thing as my v naught x squared. But that tells me nothing. I've learned nothing new. So I can't use this equation. I'm going to use this equation. Delta x is equal to v naught xt, and that's all I'm going to write. Why? Because this is 0, as we already said. Acceleration is 0, therefore this whole term is 0. What can I figure out from this equation?
Time.
Time. Time is equal to delta x. Right now, time is being multiplied by v naught x, therefore I'm going to divide by v naught x on both sides. Distance over speed. All right, all it says is distance is speed times time, which is what you knew from 6th grade. Therefore, time is equal to distance over speed. We plug it in. Our distance is, well, how far is it going? 75 meters. And how fast is it going? 100 meters per second. What happens with my units? Meters cancel out. Top of the top, top of the bottom, they cancel out. Bottom of the bottom, therefore it comes up top. We're left with seconds. All right, that's what I'm looking for. Excellent. A little larger. Left with seconds. And we do our math. 65 divided by 100 is what? 0.75 seconds. So, from this information, because that bullet hits a target that's 75 meters away, and it's traveling at 100 meters per second, it only takes 0.75 seconds to hit the target. Question becomes, how far does it fall in that 0.75 seconds? Far it falls is the y-axis. That means we need to come back to our y column over here. Which equation am I going to use now that I figured out that it takes 0.75 seconds to hit the target?
First equation.
First equation. All right, that's the one I'm going to use. Delta y is equal to, oh, well, before I do anything, what can I do? I always say plug in what? Plug in your zeros. Do I have any zeros I can plug in? I think I do. B naught. My B naught was 0. So plug in that 0. Don't you have to worry about it. Delta y is equal to 1/2 AYT squared. And I'm looking for what in this case? Hey, I'm just looking for delta y. So it's already solved for. We're good. Delta y is equal to 1/2. My acceleration on the y-axis is negative 9.8. I'll actually use it this time. Right from negative 10. My acceleration on the y-axis is negative 9.8. The time that goes by is it's ugly. 0.75 seconds. I'm going to square that. 0.75 squared, no idea what that is. 0.75 squared, 0.75. Divide that by 2, or times 9.8 rather. 9.8, and then divide all that by 2 because it's 1/2. All right, it looks like it falls about 2.75 meters. Yeah, that seems about right. 2.75, 2.76 meters. Where did I mess up? What am I forgetting? Is that 2.76? What's wrong with what I just said? It fell 2.76 meters, negative 9.8. Right. So that is the answer. Boom. Yes, we went through all that to answer this one question. All right, so to recap, we have a guy shooting a bullet with that's 75 meters away from the target. The bullet comes out at 100 meters per second. Yes, it is true that on the inside of the gun, the bullet did have a force that caused the bullet to speed up. The bullet was stationary. The bullet was 0 meters per second while it was inside the gun until he pulled the trigger. Once he pulled the trigger, it accelerated, but once it leaves the gun, that spring can no longer accelerate the bullet. Therefore, this is the free body diagram of the bullet when it leaves the gun. Okay. The only force acting upon it is gravity. Gravity is pulling it down at 9.8 meters per second per second. He didn't shoot at an angle. He shot it directly horizontal. That means that all of my velocity, 100 meters per second, is on the x, and none of the velocity is on the y, 0 meters per second on the y. You can use common sense to think that, but the math also works out as well. The same math for any vector. Break it down to the x component with the cosine, break it down to the y component with the sine. Okay. That means that, gravity is only acting on the y-axis, negative 9.8. Gravity is not acting on the x-axis. That means the acceleration on the x-axis is 0. You can see it with this, and yes, they're probably going to ask you to do something like this in the test tomorrow. You can see it with the arrows going to the right, the x-axis stays the same, and the y-axis gets smaller as it goes up, and it gets larger as it comes down, because it's negative 9.8. Okay. You always always draw a picture first. After you draw a picture, draw a free-body diagram. After you draw a free-body diagram, write down everything you know. Okay. This is everything that we knew. It asks us to figure out the delta y. You had to read the problem carefully to figure out, hey, what's it asking us to find? It's asking us to find the delta y. How far does the bullet drop? That's a delta y. Okay, cool. What equation has delta y in it? Delta y is equal to v naught t plus 1/2 at squared, and also v squared is equal to v naught squared plus 2a delta y. We concluded that we cannot use either of these equations because both equations have two unknown variables. The delta y is unknown. That's good. We're looking for that. But in this one, the t was unknown. Our delta y was unknown down here. Okay, good. That's what we're looking for. But our final velocity is unknown. Can't do anything with that. When you have two unknowns, you got to figure out something else. Luckily, we have our x-axis as well. The unifying variable between x and y, nothing is the same. All right, the x is completely separate from the y, except for time. All right, when I tried to use this equation down here, I found out nothing. All right, because there's nothing new to learn from this equation. But this equation up here, I can find out time, because this equation has a variable time that is in both the x-axis and the y-axis. So I solve for time. There is no acceleration on the x-axis. Always plug in your zeros. That means that this equation down here, distance is speed times time. Solve for t, 0.75 seconds. Plug the t in over here. Boom. If you do it correctly, you get that falls 2.76 meters. Got it? Or any questions?
I think I get it. I just about the negative acceleration.
What about it?
Okay, I think I understand it. Like, it's going in a negative acceleration because of it's going downward, or is it always going to be a negative acceleration?
It is always going to be negative 9.8 when you're doing kinematics. All right, because the Earth is always pulling it down. Okay. Now, with this up here, though, if I'm drawing a free body diagram, if I'm just trying to get the weight from something with gravity, all I do is to say, let's say the bullet is a very heavy bullet, 2 kilogram bullet. Okay. All right, which is 2 kilograms times 9.8. We don't worry about the negative in this case because you don't have negative weight. Okay. But every other time, gravity is negative 9.8. Got it?
Yes.
Okay, cool. Other questions? That was a good question. Cool. Let's see who else still here. I think everyone's still here. Yeah, everyone's still here. Excellent. Now, let's do one more before we call it quits. We've done a vector. We've done vector / forces problem up here. We've done vector / kinematics problem down here. Now we're just gonna do a straight up forces problem. All right. And that's going to be this guy right here. Okay. Now I don't like that problem, so I'm just going to make the problem right here. This is called an Atwood machine. An Atwood machine is simply a pulley. All right, think of it like the blind justice, blind justice. The little statue I'm talking about. All right, it's kind of like this. All right, right here. They both. If I can just copy this picture, copy. Paste. Copy image. Paste image. There we go. All right. Then also let's get an Atwood machine. Copy image. Okay, I'll just erase this guy. All right. So, just like with the scales for justice, right? You weigh the evidence. If this guy is heavier, it goes this way. If this guy is heavier, it goes this way. Okay. Same thing over here. All right. If this guy is heavier, it goes this way. If this guy is heavier, it goes this way. Okay. And they will both, if they weren't connected, all right, let's say I cut the wire. Okay. Say I snip the wire. Cut. If I cut that wire right there, they're both going to fall at what rate? Negative 9.8. Okay. But the wire is not cut. The rope is not cut. Therefore, they are pulling on each other. They're going to fall at a speed less than 9.8. Greatest gravity can be on Earth is 9.8. That's it, 9.8. These two forces are going to work against each other, so they're going to slow each other. They're going to slow each other down. Let's pretend we don't know which one's actually heavier. Let's pretend that this guy is heavier. Let's pretend that M2 is heavier. I'm making it bigger. Trying to make it bigger. Oh, that sucks. All right. So since M2 is bigger, I'm going to say that it's this way. Since it's rotating this way, I'm going to say that this way is positive, and this way is negative. Okay. If this guy was bigger, I would say that this way is positive and this way is negative. Doesn't really matter. Axes are imaginary. Okay. Going back to over here, we have X and Y axis. We broke down everything into the X and Y axis. That's just one way of breaking it down. Okay. Over here, I have a rotational axis. All right. It rotates this way. That's positive. It rotates that way. It's not a straight line. It's just the axis of rotation. Okay. There's another axis. We had the inclined plane. We have the perpendicular to the plane axis. We have the parallel to the plane axis. This is perpendicular. Sorry, I got that wrong. This is perpendicular. This is parallel. Remember, axes are just imaginary lines. So I'm going to imagine that this is a positive rotation. This is negative rotation. All right, cool. Got it. This is an Atwood machine. I have 2 blocks. That means I'm going to have 2 free body diagrams. This is M1. This is M2. What forces are acting upon M2? Well, automatically, you know what force is acting upon it? Gravity. And I always label my forces. This is mass times gravity. But hold up, there are two masses. Let me make sure I label this M2G. What other force is acting upon this block, M2? Someone help me out here. What other force?
Sorry.
Say again?
I said sorry. What did you ask? Like, what other force is acting on the
This yeah, so I have gravity pulling this block down. What other force is acting upon this block?
normal force or the applied force?
Okay, the force that's doing it, that's pulling it up, right? That's
Uh-huh.
better for me. Okay. It's not a normal force because normal force comes only from a surface. And it's not, you could call it an applied force. But whenever we have a rope, we call that force capital T. What's the capital T stand for?
Friction
Not friction,
force.
Tension.
tension, tension. Whenever we have the force in the rope, we call it tension. Okay? We have the weight of the block going down, and we have the rope pulling it up. And that's it. Nothing else acting upon it. Likewise, over here, we have the weight of the block pulling it down, M1G, and we have tension pulling it up. This is the free body diagram for this guy. This is the free body diagram for this guy. Okay. Now, I will go ahead and I will tell you they both have the same acceleration. If they didn't have the same acceleration, well, then one guy would be moving faster than the other, and you know that's not the case. You know that's not the case. Otherwise, the rope would break. So then, they have the same acceleration. I have a free body diagram. Whenever I have a free body diagram, it's never a bad idea. In fact, it's always the correct idea to write the sum of all forces, the net force equation. All right, the net force for block 2. All right, I said that this is the positive direction. What force is causing it to go in the positive direction? What force is acting, causing this block to go into the positive direction? Well, there's only two forces acting upon it, tension and M2G. What force is causing it to go down in the positive direction? Or rather, rotate in the positive direction. Killing me without responding. M2G. Okay.
Wait, what was your question?
What is the force? So if this is the axis of rotation, I said since this block is bigger, we're going to assume it's bigger. Since this block is bigger, I'm going to say it's going to rotate this way. And since it's rotating this way, I'm just going to make the math easier for myself and say that this is positive and this is negative. Okay. And so since I have a free body diagram, I'm doing a net force equation, which is the sum of all the forces. In fact, let me just write that. I skipped a step. Net force is the sum of all forces on block 2, and the sum of all forces on block 2. Well, in the positive direction, what force is causing it to go in the positive direction? M2G is causing it to rotate this way, and we have said that this way is positive. Therefore, I have M2G. The weight of the block is causing it to rotate in the positive direction. Make sense? What is causing it to rotate? What's acting against it? Well, the tension is acting against it. This is positive, this is negative. So my net force equation, the sum of all my forces, the weight of the block is positive, and the tension is negative. Can y'all still hear me all right? People dropping out.
Yes.
Okay, cool. All right, so this is the sum of all my forces on this guy. Let's go ahead and do the net force equation for block 1, which is the sum of all forces for block 1. And the sum of all forces for block 1, well, these are the only two forces acting upon block 1. I have the weight of block 1 pulling it this way, and I have the tension in the rope pulling it this way. Question: what is the sum of all the forces on block 1? What do I write down here?
Mg plus.
Well, ask yourself which one is positive and which one is negative. For this block, which way is positive? Up is positive. For this block, down was positive. All right, we're on two different sides. For this block, it's going in the negative direction. It's going downwards rather. And we said that this way is positive. So the weight is causing it to go positive. For this one, the weight is causing it to rotate this way. So the weight for this guy is negative. But what's pulling it up? The rope. The tension is pulling it up. Therefore, I'm going to have tension is positive and the weight is negative. So over here, weight minus tension, the weight is pulling this guy down and the tension is slowing it down. Over here, the tension is pulling it up, which is positive, but the weight is slowing it down. So weight minus tension, tension minus weight. Yes? Because we have said that this is positive and this is negative. If it were the other way around, if this was positive and this was negative, it will be reversed. All right, so then, got more people joining. There we go. My net force is equal to the sum of all forces, but what is, and my sum of all my forces is that right there. But what is net force also equal to? What is net force always equal to?
Mass times acceleration.
Mass times acceleration. Boom without this, FMA. Therefore, the net force on my block 2 is the mass of block 2 times its acceleration. Okay. And the net force on my block 1 is the mass of block 1 times the acceleration. So I have net force is equal to this, and net force is equal to that. What can I do? I can set this guy, which is mass times acceleration, is equal to the sum of all forces, m to g minus tension. My net force is sum of all forces. Net force is mass times acceleration. Sum of all forces is these two guys put together right there, m2g minus tension. So I just set M2A, boom, is equal to this guy right here. And I can do the same thing on this side. What am I going to write down over here? Am I writing down on this side? I have net force on block 1 is sum of all forces on block 1. This is the sum of all my forces on block 1, but net force is also mass and acceleration. What do I write down?
MA equals T minus MG.
M1A is equal to T minus M1G. Good. Okay. Now, I know, let's just say I know what mass 1 is. Okay. M1 is equal to 2 kilograms, and M2 is equal to, let's go, 8 kilograms. All right, doesn't matter because we don't plug in numbers. All I'm doing is saying that you know what they are equal to. We don't plug in numbers into the ends. That's proper physics. So in other words, I know what my M2 is. I know what my G is. Do I know what the actual acceleration is? No, I don't. And do I know what the tension of the rope is? No, I don't. I have 2 unknown variables. I don't know what my acceleration is over here, nor do I know what my tension is over here. I don't know what my acceleration is over here, or the tension is over here. However, I do know, I already told you, that they both have the same acceleration, and also they're connected by the same rope. Therefore, the tension must also be the same. So that means that A and T over here are the same as A and T over here. I have 2 unknowns, but I have 2 equations. And if you remember your algebra 1, if you have 2 unknowns, you have to have 2 equations. And that's what we have. So let's do it. I have this equation over here. Whenever I have 2 unknowns and 2 equations, I solve for 1 unknown variable and I plug it into the other. I'm going to go ahead and solve for tension. All right. Tension will be equal to what's tension equal to in this case? Add a T, subtract the MA. M2G minus M2A. All right, everyone see that? Move that to that side, move that to that side. I now know what my tension is equal to. What can I do? I can take this guy, plug her in right here. Which means I have M1A is equal to, parentheses, M2G minus M2A, close parentheses, minus M1G. Okay. What can I do from here? Well, this is not multiplication or multiplication or division. All I'm doing is adding or subtracting this from that. So I just go ahead and I say M1A is equal to M2G minus M2A minus M1G. And I know what my G is. It's negative 9.8. I know what M1 is. I forgot what I said it was, but it doesn't matter. I know what M2 is. What am I solving for? What don't I know? I don't know my acceleration. What can I do? let's get all of our accelerations to one side. How about that? I'm going to move this guy plus m2a over here. That means I have m1a plus m2a is equal to m2g minus m1g. I have m1a plus m2a. I'm trying to get a by itself. What do I do? What do I do? And I have factor out the a. I have a parentheses m1 plus m2 is equal to m2g minus m1g. I still want to get a by itself. A is being multiplied by this sum right here. That means that a is equal to m2g minus m1g all over m1 plus m2 to make it 100% complete. A is equal to, I can factor out g on this side, g m2 minus m1 all over m1 plus m2. And it doesn't matter. I'll keep it simple for you. m2 plus m1. Okay. This right here is always going to be the equation for an Atwood machine. Okay. This is always the equation for an Atwood machine. For the acceleration of an Atwood machine, rather. Okay. Whenever I have a block tied to another block on a pulley machine, if they weren't connected, they would both fall at 9.8, or rather, they would both fall at G. But since they are slowing each other down, they're going to be multiplied by some fraction. And that fraction is the difference in the masses divided by the sum of their masses. All right, and the bigger number always goes first. So you may or may not have to do this on the test tomorrow. Well, not tomorrow, it's Tuesday. If you don't, just remember this right here. The acceleration of an Atwood machine is equal to gravity. You know it can't be greater than gravity. Gravity on Earth at most is 9.8. All right. These would fall at 9.8, but they slow each other down. So gravity would be 9.8. If they weren't connected, but they are connected, so we multiply it by a fraction. That fraction is equal to this right here. Let's try it out. We have A is equal to G. Let's put G for now. The masses are, what are the masses? What did I say? I said 8 and 2. I'm going to put 8 kilograms minus 2 kilograms all over 8 kilograms plus 2 kilograms. Um, 8 minus 2, G is times 8 minus 2 is 6 over 10. All right, so 6/10 of gravity. Notice I don't have kilograms on the inside. Why? Kilograms minus kilograms. Hey, those can be subtracted. Kilograms plus kilograms. Hey, that can also be added, or rather, I can just do this right here. Kilograms over kilograms, what happens to those kilograms? They cancel out. All right, which is great because I am looking for acceleration. Acceleration is in meters per second per second. Gravity is in meters per second per second. So that's what I have. I have acceleration is equal to 6/10 of gravity. Or 3/5 gravity. 0.6 gravity. How about that? A is equal to 0.6 G. If G is equal to 10, about 6 meters per second per second. Got it?
Yeah, I think I have it down. So basically, these are like like this is how you find the acceleration of like two different masses when you have let me say the friction and the tension there.
Yes.
I mean,
Yes. We haven't done any problems at all where there's friction on an Atwood machine. Okay. They've all been frictionless, and I seriously doubt there's gonna be a test question where there's friction on the Atwood machine. Okay. Yeah. But if there is friction on the Atwood machine, you will just do a free body diagram like we did up here. Okay. You have tension going up, and you have friction going one way or the other. Okay. Friction always acts opposite of motion. So you'll just draw the free body diagram and include friction in the net force problem. So down here, we only had weight pulling it down and tension pulling it up. If we also have friction, this is hypothetical, I would say minus friction on that side as well. But we're not gonna have friction on this test, so let's not even worry about that. Well, sorry. We are going to have friction on the test, but it won't be part of this problem. This type of problem, rather. Also, if I wanted to figure out what the tension was, what would I do? I would have to use this equation right here. I would have to use this equation right here. So I would solve for acceleration. Boom. And I would plug acceleration back into this equation up here. Got it?
yes.
All right. Good stuff. Are there any questions? There's still more there's still more that we could cover, rather. Like we haven't done an incline problem. We haven't done a problem like this, but that was the entire lab, and which is due tonight, I believe. So let me give y'all time to go do that. Are there any questions before I let y'all go, though? You can ask me questions about the lab too. If you have questions, I'll try to answer them if I can. All right. Well, I hope tonight was helpful. Was it helpful? Y'all learn anything?
Yes.
Excellent. All right. I record this video. I'll put the notes on Schoology, and I'll try to upload the video as well. All right. Cool beans. Y'all have a wonderful night, and I'll see y'all tomorrow. No problem. Thank y'all for coming. Thank you. Thank you, everyone who came. Sweet.